We'll be continuing Chapter 2 on functions and graphs. And today we'll be talking about transformations of functions. So transforming the graph, making it go up, make it go down, make it enlarged or smaller. The objectives are to recognize graphs of common functions, use vertical shifts, that's up or down, use horizontal shifts to graph functions, use reflections, use vertical stretching and shrinking, use horizontal stretching and shrinking, and graph functions involving a sequence or combination of transformations. So these are the most common ones that you're going to want to memorize what the original graphs look like. So f of x equals c, that just means c is a constant. F of x equals some x. F of x equals the absolute value of x. F of x equals x squared. F of x equals the square root of x. F of x equals x to the third. And f of x equals the cube root of x. And I would just look at those graphs and memorize what the original ones look like, which will be on the next slides. Okay, f of x equals c is the constant function, so the c you can think of as constant. The domain is negative infinity to positive infinity, so the x goes from negative infinity all the way to positive infinity. The range is wherever the c is at. The function is constant on that negative infinity to infinity, and it is even because it can reflect across the y-axis. So this one looks like it's hitting about 1.5. So this would be f of x equals 1.5, or you may have seen this as y equals 1.5. So you just notice it's a horizontal line, but it is a function because it does pass the vertical line test. F of x equals x is known as the identity function, and the domain and range are both negative infinity to positive infinity, so it goes forever and ever in the negative direction to the positive direction, and it is odd because you can reflect it over the origin, and we learned that in the last lesson. Reflect over the origin. So you may have seen this before as just y equals x. And in past math classes, we said you can put a 1 in front of this. This number is the slope. So it just has a constant slope of 1. It's going up gradually in the positive direction. Okay, the absolute value of x, you're going to notice, looks like a v. And again, this goes from negative infinity to positive infinity for the x values. The range is just from 0 to infinity. So this is the possible y's. So you notice it starts at 0, but then it goes forever upward. So if I kept stretching this out, it's going to go all the way up to 100, to 500 on the y, to infinity on the y. It's decreasing from negative infinity to 0, and then it starts increasing again once it hits that 0 to positive infinity. And it's even because it can be reflected over the y. If you ever forget what these should look like, you could always make a table of values and then plug it in. So instead of f of x, I put y, but you could put an f of x there if you wanted. And then your coordinate pair. So for example, when x is 0, the absolute value of 0 is just 0. So we have that coordinate right here. For 1, I'd have y equals the absolute value of 1, which is 1. So 1, 1 is a coordinate, which you can see is right here on the graph. And then let me do a negative number. The absolute value of negative 1 is also 1. So our coordinate is negative 1, 1. So that's why it makes this v, because negative 1, 1 is right here. So it ends up making a V because we're not going to have any negative values because the absolute value will not give you a negative distance. Okay, x squared is a parabola. This is a quadratic function. And that goes from negative infinity to infinity for the x values. And the range again is going to be just from 0 up. Because if I took just some numbers and squared them, if I did 1 squared, I'm going to get 1. If I did 2 squared, I'm going to get 4. But if I do negative 2 and I square it, I'm also going to get 4. So that's why this one also only goes up in the positives. So 1, 1 would work. Negative 1 squared is 1. Then you'd have 2, 4, which I can't fit on this graph, and negative 2, 4. So it decreases from negative infinity to 0, and then it increases again once you hit 0. Then it goes upward. And this is also even. The square root of x, this is what it kind of looks like, a little curve. And again, square roots are only positives. So that's why we're starting at 0 and going to positive infinity. It's not odd or even because it does not reflect over the y-axis or over the origin. And you could do a table of values to understand this, but you're never going to take the square root of a negative number. You cannot do the square root of negative 4. You're going to get error on the calculator. So we can only do square roots of positive numbers, and you're going to get those positive numbers as a result. And when we do this, we only care about the positive version when we're graphing. So the square root of 4 ends up being 2. So we're not going to be down in the negatives at all. Then x to the third, it's kind of like a little wave. It curves a couple different times. So this goes from the negative direction all the way to the positive direction for the x's and the y's. And it's increasing the whole time because it's technically, if you started down at negative infinity, it's increasing the whole time. It does look like it gets pretty constant, but those are just very small values in there. And it is odd because it reflects over the origin. And then the cube root of x, it looks kind of like the last one where there's that double curve, but it's a little different shaped. And again, that goes from negative infinity to positive infinity. It is odd because it's reflected over the origin. And then I included this in your slides just so you have a good resource to look back at. I actually have a lot of slides just with pictures so that you can print these off and use them to study. The book is a great resource on this, so you can go to section 2.5 in your book and look at all the pictures in there. I think they're very helpful when you're trying to understand these. So we already talked about these 3, and then we talked about these 4, so when they're all next to each other you can see a little better how they are related and how they are different. Okay, a vertical shift is when it's going to go up or down. So we're going to let f be the function and c is a positive real number, some constant number. So the graph of y equals f of x plus c is the graph shifted some amount upward. So if this was a 2, you would shift it upward 2. So that's when you're adding c. If you're subtracting c at the end, it's going to go downward, however many numbers your c is. So here's an example. I have plus 3. So my original one is in blue here. That's that V shape. And you can see I have 1, 1, 2, 2, 3, 3, 4, 4. But then it goes the same on the other side because the absolute value of negative 1 is still positive 1. The absolute value of negative 2 is positive 2, etc. Then the red one is if we add 3 to the end. So you notice it started at the origin, then I went up 1, 2, 3. So now my graph is starting there, but everything else is the same. So you're going to have the same slope. You're going to be going up 1 over 1, up 1 over 1. So the V should match. The original V is just shifted upward 3. Okay, horizontal shifts are when the C is on the inside of the parentheses. So you can see that it's on the inside of the parentheses. So this is going to shift it left or right. So the difference between this one and the last one is the C is inside the parentheses. So this you have to kind of think reverse. So if you're adding C, you're actually going backward or left that many. If you're subtracting C, you're going to go forward or right. And you can make a table of values to see why this works. But this pattern is always going to happen. If you're subtracting the C on the inside, it's going to go forward instead of backwards. So you have to think opposite of what your brain's probably telling you to do on these. So here's an example. Now this isn't parentheses, but it is a grouping symbol. So it doesn't have to be parentheses. It just has to be where the number is inside some grouping symbol with the letters. So it's inside. It's -4. So again, you have to think opposite. I'm going to be going forward 4. So my blue is the original square root of x. And then if I add 4 or subtract 4 on the inside, the shape is going to stay the same, but I'm going to shift it forward. So it went 1, 2, 3, forward 4, and this is the new starting point instead of the origin. So usually you can just start at the origin with your original and then shift it however much it tells you to. Okay, and here's another one I thought the book described very well. So you see the 5 is on the inside of the grouping symbol. So the square root of x plus 5 is going to be the same shape as the square root of x. You're going to go left or backwards 5. So if it's plus 5, you have to go backwards 5. So you notice it started at the origin, but then my new graph, I have to shift it backwards 5. So now it's starting back at -5. And what you can do here is subtract 5 from every x coordinate because I'm shifting it backwards 5 on the x-axis. So it was 0, 0. If I subtract 5 from my x coordinate, I get -5, 0. I had +1, +1. So if I subtract 5 from the x coordinate, I get -4, 1. The y coordinate doesn't change. So that's where they got this coordinate. And you could do that with every coordinate to easily shift it. Okay, now if you want to combine a vertical and a horizontal shift, let's look at this one. So it doesn't really matter which order you go in on this one, but it is going to be easier if you move it backwards or forward first. So this +1 means I need to go left 1. So I'm going to subtract 1 from each x coordinate. So it started at the origin. Now I shifted it back. And it is a parabola because of this squared term out here. And the 1 is on the inside of the parentheses, so that's why I'm going left instead of up. And now for the -3 part, that means I'm going to go down 3 units. So I was right here. That's where I was. So I have to go down 1, 2, 3. So you could subtract 3 from your y since you're going downward. Okay, now we'll talk about reflection. So if you want to reflect it over the x-axis, you notice the negative is on the outside. If you want to reflect it over the y-axis, the negative is on the inside. So we're comparing the original parabola graph, and now if I put the negative on the outside, it reflects it over the x-axis. It makes it go upside down. But everything else stays the same. So you notice the y just became its opposite on all of these. But the other numbers stayed the same. Okay, here's one over the x-axis. So on this one, again, we have the negative on the outside. And so it's going to just flip it over, which on this one, you could maybe look at this first. It's kind of easier to do it in pieces, and then if I flip it over the x-axis, it's going to look like this. So you notice the y-coordinate became its opposite. And if I look at the other half of the graph, and if I flip that over the x-axis, it ends up being upside down over here. So it's a little easier if you go in pieces on this one, and you notice the 2 here became a -2 when we flipped it over. Okay, now over the y-axis. So this time the negative is on the inside of the grouping symbol. So if I look at my blue one, that's the original. So here's my original for cube root of x. Now this one's kind of deceiving because it actually looks like it's reflected over the x as well. And it actually is, but that's because it's a double curve. So if I look at this, let me do it in green. If I just look at this piece, the reflection we're looking at is over here. That got reflected over the y-axis. And then this original piece got reflected over here. Okay, and here's another y-axis one with just one curve, so it's a little easier to visualize it. Negative is on the inside. This original square root of x looks like this blue graph. And then I'm going to reflect it over the y-axis. So I'm going to replace each x coordinate with its opposite. So it was 1, 1, now it's -1, 1. It was +4, 2, now it's -4, 2. And the origin stays where it's at. Okay, now vertically stretching and shrinking. So this time we're going to be multiplying by something. So the c is on the outside of the parentheses. We're going to multiply all the coordinates by the c. So the stretching one down here, you can notice the original was the blue. Then the purple got stretched. It got pulled up. So now it's actually a narrower graph. Then if I look at the next one, so this was if c was greater than 1. If c is between 0 and 1, so a fraction, between 0 and 1, or a decimal, the c is still on the outside. This is going to make it vertically shrunk, which actually makes it wider. So you notice my blue one down here. If you look at the blue one, when I have the purple graph multiplied by c on the outside, it actually makes it shorter and wider than compared to the other one's shape. So we'll look at some examples because the narrower, wider part can get a little confusing when you're looking at the curves. So I think this one's one of the easier ones to understand. So if you look at the black, that is my original x squared parabola. And again, if I think of a table, If I take 1 squared, I get 1. 2 squared is 4. 3 squared is 9. So that's where they get the 1, 1, the 2, 4, then 3, 9 would be up here somewhere. Then if I make it multiplied by 2, it actually makes it narrower. It pulls it up. And then the purple one is multiplied by a fraction less than 1. It's 1/2. So this one is actually the widest graph. And that's because I'm multiplying essentially all these by a half, which is making them smaller. So it's stretched differently on the axis. So like if I did 4 and cut that in half, that puts me at 2, 2 instead of 2, 4 now. So this coordinate becomes 2, 4, or 2, 2 instead of 2, 4 is what it was. Okay, here's another one where a 2 is multiplied on the outside. So my blue is my original absolute value V. And then if I multiply it by 2, it makes it that red graph, which is narrower than the original. Okay, now this time the C is on the inside of the parentheses. So you notice that here. So if C is greater than 1, it's going to be horizontally shrunk by dividing each x coordinate. If the C is between 0 and 1, a fraction or a decimal, it's going to be horizontally stretched by dividing each of its x coordinates by C. So you can see the original blue one, and then it got horizontally shrunk that purple one is shrunk when I put the C on the inside. And then the stretching one, the original, is smaller than the one that was stretched horizontally. So here is another example. The half is on the inside of the parentheses. So my blue one is the normal parabola. And then when I multiply by 1/2 on the inside, it's going to make it stretched out. So the red one is wider than the original one. Okay, here's another one to look at. So you notice the 2 is on the inside. So we're going to horizontally shrink by dividing each x coordinate by 2. So if I look at my -2, 4, if I divide the x by 2, I get -1. So that's where they got this -1. If I look at 4, 0, if I divide the x by 2, I get 2, which is where they got this. So you can see it got shrunk. It was a pretty wide blue graph, and now it's a smaller purple graph. Okay, and this time it's multiplied by 1/2 on the inside. So when you divide by 1/2, it's actually the same as multiplying by 2. So it actually makes it larger. So if I would take -2 divided by 1/2, if you remember fractions, you have to flip that second number and turn it into multiplication. Keep switch flip. So you actually get -4. So that's where they got this number. So if you're dividing by a fraction, you actually end up multiplying by the reciprocal of that. Okay, we're going to end with some transformations with a series. So we're going to combine a lot of steps into one. So I'm taking my original f of x formula and I'm doing all this to it. Okay, so what we usually do first is look at the parentheses. So look at the part where the x minus 1 happens. And that's going to cause us to move it backwards 1 unit to the right. And then this 1/2 out front, we're going to ignore the negative for now and just look at the 1/2. The 1/2 shrinks it because you're multiplying by 1/2. Now that negative is going to make it flip. So you're going to reflect it over the x-axis. So if the negative is out front, it flips upside down. And then that plus 3 on the outside makes it go up 3. So we're going to look at some pictures here of what's happening on the next slide. Okay, so step by step. Remember we said that -1 on the inside causes it to go forward 1. So if I look at my origin here, this is my original graph that I'm going to use. So they would have to give you what it needs to start at. So this is the original graph they want you to use for f of x. So then I moved everything forward 1. And to do this, you can just add 1 to each x coordinate. So you notice this -4 here turned into a -3 here. And now this 1/2, we're going to shrink it by a factor of 1/2. We're going to multiply each y coordinate by 1/2. So if I take 4 times 1/2, I get 2. And then you keep doing that pattern. If I take -2 times 1/2, I get -1, and so on. So you notice it vertically shrunk it. It got shorter than it was. So now we're going to take this green graph and transform that into the next step. So from the green graph, now I had to look at my negative out front, and that causes me to reflect it or go upside down. So you turn the y coordinate into its opposite. So on the last slide, we had the y coordinates were opposite. So this 3, 1 was down here at -3, -1, or -3, 1. Or sorry, 3, -1. I'm getting my negatives in the wrong spot. So I looked at my y and I made it into its opposite and flipped it over the x-axis. And then finally we have our plus 3. That's the easiest. We're going to just add 3. We're going to shift it up. So like this point right here is going to be shifted up to right there. This point right here, I'm going to shift it up here. So you notice I had a 1. If I add 3 to that, that's where this 4 comes in. So I would just definitely look back at these, study them, see what happened along the way. There's a lot of different steps involved. Okay, we'll do one more series of transformations. So this one, there's a 2 on the outside, a 3 on the inside, and then a -1 on the outside. And this is a squared formula, so it's a quadratic. Okay, so let's look at the parentheses first. Plus 3 means on the inside we're going to go backwards or to the left. Then we have the 2 on the outside. We're going to multiply everything by a factor of 2, which is going to stretch it. Then we're going to shift it downward because of this minus 1, we're going to go down 1 unit. So we're comparing it to our original parabola. So the blue is the original parabola. And we're going to start with the parentheses here. We have plus 3 on the inside. So that means we're going to go 3 units backwards or to the left. So if I was here, now I'm here. If I was at negative 2, 4, now I'm at negative 5, 4. So I'm subtracting 3 from the x coordinate. Okay, then this 2 on the outside means I'm going to multiply each y coordinate by 2. That stretches it vertically. So you notice this negative 3, 0, that doesn't change, but our negative 5, 8. On the last slide, we had negative 5, 4. So it was down here. And now it's stretched it up. So I multiplied this by 2 to get the 8. And we did that with the other coordinate to get this one as well. And then finally, the minus 1 on the outside means we're going to shift it down 1. So we're just going to subtract 1 from the y. So if I was here, if I take 1 away, I'm going to be at negative 3, negative 1. So you notice it shifted down. If I take 1 away here, I'm going to be at negative 1, 7, which is right here. Okay, so again, please print these off, study them, look at your book examples in 2.5 if you need more help. And I think practice is going to be the main thing that's going to help you on this.